everyone. So we'll be doing two awesome tests here as we continue these series tests. The alternating series test, and we'll also be doing the ratio test. So with this alternating series test, that series, we're going to start at 1, starts at 0, whatever it is, you'll notice that, or maybe -1 to an m plus 1, or maybe a -1 to the n minus 1. One of these things you'll see in a series, that's going to make the series alternate. I'm going to put this on all three of these. That's what you need to focus on so that you know that, hey, perhaps, I'll say the word, perhaps we can use the alternating series test. Because this is what makes sequences alternate. And then maybe over here it has, 2 to the nth over n cubed, or n plus 5 over n plus 2, something extra. But I wanted you to realize what's making these series alternate. It could be anything like this. -1 to the n minus 1, -1 to the n plus 1, or maybe just -1 to the n. And that's what we call an alternating series. And yeah, I guess you're saying we're thinking, if I see this in a series, I guess I can always use the alternating series test. Not exactly, because this test, I want to emphasize one thing, it only shows convergence. So it's not like many of these tests we've done, like the geometric series test, but it has this, it converges, this, it diverges. Integral test. In this scenario, it converges, in this scenario, it diverges. This test is only used to show convergence. So if we don't have a proper setup, then we'll just go to something else. And I'll explain exactly what you probably want to go to. We'll talk about that. So this is what will make it alternate, but you may have stuff like, oh gosh, it could be just, here's something like, let's say we have a 1 over 2m plus 1 in the whole here. I see whenever. I'll do 5m plus 3, or the 6m plus 1. So about n cubed. These are just 3 examples of the kind of stuff we'll see. But maybe we can use alternating series test on this. So what has to hold? 2 things. First of all, we got to make sure that the terms of the sequence decrease. That's the first check. We got to make sure that the terms of the sequence do decrease as n approaches infinity. So when we write this stuff, do you remember every time I wrote a sequence, I referred to a sequence as a sub n, the sequence portion? So let's refer to like all this here as a sub n. But the portion after that -1 to the n minus 1, that 1 over 2m plus 1, let's refer to that as b sub n. So that we're organized when we're doing this test. So this 1 over the 2m plus 1 will be b sub n, but a sub n will also include the -1 to the n minus 1. So same thing here. All this will be a sub n, but let's refer to b sub n as the 5n plus 3 over 6m plus 1. Or in this example, all this right here, we'll think of the sequence as a sub n, but just the n cubed over 3 to the nth we'll refer to as b sub n. Cool. And the 2 things, this is a great test, because you're pretty sure you're going to try it every time you see a -1 to the nth or -1 to the n plus 1. 2 things have to hold, the terms have to decrease as n approaches infinity, and then the limit of b sub n just has to equal 0. And that's it. It's a pretty cool test to try, but if the limit's not equal to 0, we can't use it. See, that's what's going on. You'll see a lot of these, the terms are going to decrease. So let's look at this one right here. We'll start with this one. -1 to the n minus 1 times 1 over 2m plus 1. And it's kind of like number 5 from the textbook. Do the terms decrease? Are the terms of b sub n decreasing? I say yes, do you agree? 1 over 2 times 1 plus 1 Then you put 1 over 2 times 2 plus 1, 1 over 2 times 3 plus 1. What are those terms? You can just look at them. It would be 1 over 3. What would be the next one? When you plug in a 2? 1/5. 1/5. Aren't they getting smaller? So that holds true. But we do have to make sure the terms are decreasing. Now, what's the limit as n approaches infinity of 1 over 2, which we're referring to as b sub n? You know, in terms of b sub n. So what's the limit of this? Notice I'm not doing a -1 here. I'm only focusing on b sub n. Isn't that funny about this test? We focus on b sub n every time. Is that 0? So this series right here converges by alternating series. This series converges by the, oh, we can abbreviate, how about AST? By the alternating series. That's number 1. Great test, though. Converges by the alternating series. Have a look at that? Try to second. You put yourself in test mode too. You're like, aha, you spot this. Of all the tests, geometric series tests, integral tests, there are comparison tests. What's going to stick in your mind? Try what? Try it first because you see -1 to the end. Try the alternating series test. Give it a shot. If it doesn't work, we'll go to something else. Sound good? Let's focus on part 2. You know, I know the terms have to decrease, but what is the limit of b sub n? Before you just automatically think the limit's always 0, oh, converges by alternating series test. Everyone, I'm going to write this down. What's the limit as n approaches infinity of the b sub n? Just this part. You can do, you can think of the horizontal asymptote that exists, of that rational expression there, or you can do L'Hopital's rule. What would be the derivative of the top? 5. What's the derivative of the bottom? 6. So what's the limit? Is it 0? That's not 0, is it? Right away, can we use the alternating series test? No, we just can't use it. I mean, here's my worst fear on a test. The student goes, diverges by alternating series test. You can imagine how many times I've gotten that. Alternating series test does not show divergence. There's no divergence test. And that's why on this summary sheet, I want to point out, you see this big X I have down here? I put a gigantic X, so you're reminded that, oh, it doesn't have a divergence test. So we're going to have to go somewhere else. That's okay. Alternating series test isn't telling us whether this converges or diverges. But you know where I want you to go? If this limit's not equal to 0, I always want you to go to this test. Because I believe you'll be fine if you try alternating series test on -1 here, in terms of this sequence here. And we see we can't use it when the limit's not equal to 0, right? Then look at test for divergence. Go right to that. So I'll erase this. I can't use alternating series test. But what's going on by test for divergence? Now test for divergence, I have to think of the entire sequence. Well, one of the coolest tests, remember what that says? If the limit of this entire expression right here is not equal to 0, or does not exist, then this series has to diverge. So is the limit of this expression right here with the -1 end, is it equal to 0? No, it's bebopping between a -5/6 and a 5/6. But it does not exist. So this series diverges by test for divergence. And I'll write that down. But I want to be clear. So if you try alternating series test and you notice you can't use it because the limit's not equal to 0, go right to limit test for divergence. Go right to that. So I'm going to say that this series diverges by test for divergence. And then no, I have to somehow justify what test for divergence is, right? So let me just, it doesn't take much room here though. Because the limit as n approaches infinity. Now notice with test for divergence, I have to think of the entire a sub n. Okay? All this. And 5n plus 3 over 6m plus 1 does not exist. I look at D&E, I worry that you look at that, might say 1, so I'm going to write does not exist. Does not The reason it doesn't exist, everyone, I know this was going to 5, 6, but the negative on the end, making it alternate between a negative 5, 6 and a positive 5, 6. A negative 5, 6 and a positive 5, 6. It's not converging to a number in terms of that sequence. But the limit is just non-existent. I'll get out of the way, I don't want your copy. So I hope you love this test. You know when you're going to try it, right? You know when you're going to try the alternating series test, but if it doesn't rule, it doesn't work, go right to test for divergence. Go right here, go, hey, I'm going to try test for divergence. That's what you do. Hey, try this one. N cubed over 3dn. Well, are the terms decreasing? Let's check it out. Are the terms of, remember I call this B sub n, here, your B sub n. Are the terms of B sub n decreasing? You just got to make sure that's happening. What's the first number? 1 cubed over 3 to the 1 is what? 1/3. Now plug in a 2, what do you get? You get 8 over, what's 3 squared?
9.
And now, and I chose this problem on purpose, you may be freaking out like we can't use this test. Because when those numbers decrease, I know you're sitting there going, uh-oh, I don't know if I can use this. Did those decrease? No, so let me be clear about this. I know that this theorem, or excuse me, this series test says the terms of B sub n decrease as n approaches infinity. What we mean is this. Would you put this down in your notes? That it eventually decreases. That it eventually decreases. You could have a little split at the beginning, a couple numbers where it actually jumped up. Do you notice that went up? That number's higher than that. But let's look, a few more. This was n equal to 1. This was the second term. What's the third term of B sub n? 27 over 27. All right, 1. What's n into 4? 64 over what? Aha. Do you see what's happening? Now they're starting to go down. Try n to the 5th. Or n equal to 5. The 5th term.
125 over
125 over 3 to the 5th. 243?
Yeah.
And when these are starting to decrease, after the 1, 2, 3, after the third term. So these terms do decrease eventually. And you can keep going. What's the next number going to be? It'll be the 6th term. Well,
16.
you want to try it out? What's 6 cubed? 216? What's 3 to the 6th?
729.
See what's happening? They eventually decrease. So don't let that throw you off. I didn't want you, because I think it happens, everyone, on number 11 in the homework, in the practice problems, where maybe the first 2 terms it actually went up a little bit, like here, increased. But eventually it what? Eventually starts decreasing. So I'll make a note that these terms are decreasing after which term? After the third term. Jessica?
At what point do we stop trying to see if the equation will arrive at the
I would say when you jam these, if you didn't see it after like the first 5 terms, yeah, that would be it. So notice here it was right away. Right, that's what, 0.3? With the line over it, that's 0.2. But in some cases, I didn't want that to startle you. You're like, they're not decreasing. But these usually go hand in hand. When the terms are decreasing, these usually go hand in hand. You'll notice that the limit of the sequence is 0. Okay, so they usually go together. I could see someone going home tonight practicing this and giving up on a problem because look what they observed right here. It went up, but they eventually will decrease. That's the key, eventually. All right, so when I'm going to write this down, it started decreasing after which term? After the fourth term and beyond? All right, so I'll put n equals 4 and higher. Terms of B sub n decrease for the 4th term and beyond, right? I can use n equals 4 because we've got these n's in here. And what's the limit? I know you know this limit. The limit is n approaches infinity. And when I got a monomial, n cubed over an exponential.
0.
Right? Who wins that race? Who increases more rapidly? Exponential, right? Right? Nothing beats exponential except for
Factorial.
factorial. We were talking about L'Hopital's rule a few minutes ago. Could you do L'Hopital's rule if that bugged you? You sure can. What's the derivative of 3n cubed? 3n squared. This derivative, you may not know, we're so used to e to the x. What's the derivative of e to the x? E to the x? Well, 3 to an x, the derivative is 3 to the x times natural log of 3. But still, you could keep doing that. You'd see eventually that this right here, the limit is equal to 0. So in this series converges by what test?
AST.
Converges by AST. Ooh, you got it. It converges by AST. Awesome. Okay, I'm going to talk about this alternating series estimation theorem. There was a problem in the book, and I recall that this problem, I'll raise these. Is that okay? Yeah? Hey, if you don't see that limit going to 0, what test will you go to? For alternating series test. Now you see this in a series, or something like that in the series, and you notice the limit isn't to 0, go right to what test?
TFD.
TFD, test for divergence. All right. So and this is number 19. Alternating, right? N to the n. So look at that carefully. This is 22. This section's great. These problems go quick. We know what test we're going to try. My gosh. You don't have to do any crazy integrals. Is that n minus 1? Yeah, they got n minus 1. This one started at 1, and this one started at 1. We were just talking about this. N factorial increases so rapidly, right? We were talking about 10 factorial, and it's already humongous. Right? Your TI-84 calculators, try 70 factorial. It can't even show it. It's an overload. Did you know that? If you try to hit 70 factorial on those TI-84s, it's too big, right? But, what about n to the n? Who's increasing more rapidly? N to the n or n factorial? N to the n. So, we can't use the alternating series test. You know why? The limit's not equal to 0 base of n. Does someone see that? But, what test can we use? Let's not say, oh, diverges by alternating series test. Let's go right to the what?
TFD.
Yep, test for divergence. So this series diverges by test for divergence. Maybe that TFD looks better. Because the limit, as n approaches infinity, now I got to include the entire a sub n, negative 1 to the n, times the n to the n, over n factorial, does not exist. If you wonder what it's doing, it's bebopping between positive and negative infinity. Right? It's divergent in terms of the sequence, but it's also making the series divergent. Isn't that cool? Was that okay with that? Oh, let me go away, Julia.
Thanks.
You bet. So right away, do not write, oh, diverges by alternating series test. It only shows one. Convergence. But go right to the test for divergence. This is the one I wanted to make sure to do with you, everyone, because a lot of times on an exam, I have students who look at this and they think it's geometric. And they're going through their list and they're like, let me just do a geometric series test on this. Is this geometric? This is not a geometric series. If that n wasn't there, yes it is. If that n was not there, you got everything exponential. Does anyone see that? But you got an n over a to the n. This is not geometric. So let's definitely try this what? Alternating series test. Well, first of all, do the terms decrease? Are the terms of v sub n, the v sub n terms decreasing? Or eventually decreasing? Are they eventually decreasing? Let's check it out. What's 1 over 8 to the 1? All right. Remember, I'm just looking in terms of v sub n. This is the v sub n right here. What happens when you put a 2 in there? Oh, yeah. They're shrinking, right? Check. V sub n terms are decreasing. Jessica, okay with that? I just noticed the first 2. It's going to continue. Because you plug in, what's the next number? 3. And you got 8 cubed. What's 8 cubed? What's 64 times 8?
256.
64 times 8. Is that 512?
512.
Yeah. I mean, they're just shrinking. And what's the limit? As n approaches infinity, of an n over 8 to the n.
0.
It's 1 to 0. Exponential blowing away that polynomial on the numerator. Or do L'Hopital's rule, the derivative, this is 1. What's the derivative of 8 to the n? Natural log of 8 times 8 to the n, which is still setting that thing as 0. So this converges by what?
AST.
AST. Ooh. Hey, now we're going to do the alternating series estimation theorem. This theorem is really cool. This is an awesome theorem because now we can estimate. Have you noticed we've been trying to estimate these series lately with the integral test? The only test that gives us an exact value is the geometric series test so far, right? Well, we can estimate how accurate it is in terms of how close is it to, can we have it accurate to 4 decimal places, 5 decimal places? With these calculators, sometimes you can get it accurate to 8, 9 decimal places in terms of what you have there. All right, so what's it say? For this alternate series estimation theorem, over there I have something like this. R sub n with the absolute value bars over it, less than or equal to b sub n plus 1. This is an alternating series estimation theorem. What the heck does this mean? So, to better understand this, we'll work a problem. So, I'm going to take number 23 from the textbook. And this is what it says. About this series. N equals 1. We'll do a couple of these. N equals 1 to infinity. Negative 1 to the n plus 1. All over n to the 6th. All right. And they ask this question. Oh, hey, before I ask this question, could you do me a favor? Can you make sure that series converges? We would waste our time if the series doesn't converge, right? So can you just make sure that converges? Does that series converge? It does. See how quick you can see it? Are those terms decreasing 1 over n to the 6th? Yeah, they're getting smaller and smaller. What's the limit as n approaches infinity of 1 over n to the 6th? 0. So this series is converted by alternating series. But what we're asking here is, how many terms of the series do we need to add in order to find the sum accurate to and a given error? I'll write this down. How many terms of the series do we need to add in order to find the sum to the indicated accuracy? All right. This is the accuracy they wrote for number 23. 0.1, 2, 3, 4 zeros, and then a 5. Okay. And in front of this, they wrote, let's see, take that off here. They wrote the bars around the error. Less than. Double check with Chris about my
That is 4 zeros and a 5, right?
Okay, good.
You got a pilot eyes.
So we got 4 zeros and a 5. How many terms in this series do we have to add? So to get this thing started, we gotta start looking at all the terms. Like at n equals 1. And you can make a table. The first term, what's the a sub n? So when I'm gonna plug in a 1, what do you get? Negative 1 to the 1 plus 1 is what? 1. What's 1 over n to this 1 to the 6th? 1. Okay. Go to the next term. 2. Eventually we're going to see how far we got to get. I plug in a 2 into this thing. If you want, everyone, you can just look at the absolute values because they're talking about the absolute value there. But even if I get positives and negatives, I'll change it to negatives and positives. Nothing wrong with that. What happens if you put a 2 in this? That'd be the first term. Does everyone agree? Be careful. Sometimes these start at a 0. Have you seen that? Sometimes the series start at a 0. I'm going to plug in a 0 first, but this started at a 1. All right, that's the first term. It's a 1. What's the second term?
Negative 1 over 64.
Negative 1 to the third, which is negative 1. And then 2 to the 6th is 64. We're going to write this as a decimal, though. So, Isaac, what's negative 1 over 64? Keep in mind, we're just going to focus on the positive values.
0.01.
You take the absolute value of this. Oh, what do you get?
0.015625.
0.015625. And it was negative, right? But I don't care if you kept that positive in terms of that. I'm going to keep it negative because eventually we're going to add these up. So think of the absolute value of that. Think of the absolute value of that number. Is the absolute value of that number less than this? No. So we got to keep going. We got to continue this. So now we notice this particular problem, I think the technology is going to make this stuff easier, right? If you want to just keep doing this by hand, you can. I'm going to pull up the screen and I'm going to use the list. If you want, you can look at the list and we'll do that. But everyone, I'm going to keep going until I get the number that's lower than what? This. That's what I'm going to do. It's pretty simple, isn't it? And then I'll be very precise in how we're going to answer this question. Because it's got a, doesn't say b sub n, it says b sub n plus 1 there. Does everyone see that? So if this was like 5, this would be a 5 plus 1, 6 term right there. So let's continue, but I'm going to use technology. If everyone's okay with that. Okay if I pull it down? You sure? Thanks. Yeah, thank you. I'll pull it up. Now I'm just going to continue this, but sometimes with those G83s and 84s, you may prefer to have it in a list. Right? So I'm going to use the calculator, put all this stuff in a list. Thank you. Thank you so much. Okay, so this is what I'm going to do. I'm going to go to just a list one. So I'm going to go to stat.
Thank you.
I'll go to stat. And then I'll hit enter for edit. And now in L1, what I'm going to put in L1 is just the numbers. What is it? 1, 2, 3, 4, 5, 6, 7, 8. Just get it going. I could have gone further. I just want to see. I'm going to keep doing this until I get a number in the second column that's going to be lower than a number. So what am I going to type in the second column? I'll go over here, I'll right arrow. I'm going to up arrow into this L2 and I'm going to type, what's the formula? It's negative 1 to the n plus 1. Do I have to write that? I don't have to type that. I really just got to do the divided by the what? End of this thing. So that's what I'm going to type. I'm just going to hit 1 division, and then I'm going to hit that x variable raised to which power? Raised to the 6. And just do that. Whoops. Yeah, I was thinking x because it's like a thing, that's L1 there. Thanks, Dave. I'll go back to stat edit. Yeah, edit. So funny, because so many times you'd be doing like, using Microsoft Excel. I'm gonna hit 1 division, and I'm gonna raise, is it x to the 6th or L1 to the 6th? L1 to the 6th. So how do I get L1? Second one. And just raise it to the 6th power. Just so you can see all these at once. All right. Which number is the first term to get lower than 0.0000? That's 4 zeros in a 5. Which one is it? It's the 6th term. Outstanding. And when they recognize it, it's going to be this number right here. That says 2.1 e to the negative 5. So in the 6th term, which was, look, no, 6, was 2.1 e negative 5. That means 2.1 times 10 to the negative 5th power, right? Which is, how many zeros in front of that 2?
4.
4 zeros, then a 2. I want to make sure one can see that. I'll just pop the light up real quick. Does everyone see when this is in scientific notation, how to convert it to a decimal? So this is the first term that's lower than this, right? Well, according to the remainder theorem, what we're going to do, hey, can you read those other numbers to me real quick? What were these other numbers? What was 3?
3 was
0.00,
1 through 7.
that'll work. Number 4th term,
2.4 e to the negative 4.
negative 4. 5th term,
6.4 e negative 5.
all right. So this is what this theorem, this is awesome theorem, but this is what we do. We went through checking each number until we found the number that was lower than this value here, right? What was the first term that was lower than? Because the rest are going to be lower than it too. The first term was the 6th term. According to the theorem, what we need to do, we need to add the 1st through the 5th terms to obtain this accuracy. Let me be clear again. The 6th term was the first term that was lower than this, right? That means by this theorem, we have to add the first 5 terms to get the desired accuracy that we want. So the accuracy of adding up those 5 terms will give you an error less than or equal to this to the actual sum of that series. So hey, I want to make sure we're clear on this. What if we did another problem and it took the 11th term? How many terms you got to add up? 10, the first 10. What if you did another problem and it was the 4th term? Then to get the desired accuracy, you got to add up the first 3 terms. Does everyone follow this? That's what they mean by this n and this n plus 1. Hey, one more, I think you got it. One more time. What if it was the 7th term, was the first term that was lower than this? Then you need to add up the first 6 terms. You got it. You got it. And what I'm going to do, everyone, I'm going to delete these out and see what the sum would be. Now we'll just see. What would happen if I went in here? Let's see, I'll go down here. We only have to add which terms? The first 6 terms, right? All right, delete. Delete. Go over here. Delete. Delete. And I'm just going to hit quit. I'm going to hit second stat. I'm going to arrow over to math and get this sum button. And which list should I sum, Dave? L2. I'm going to sum L2. So I'm going to hit second 2. And when this, right here, this sum, 1.017, I'll hit the light so we can see that.
Wait, I think that's wrong because you left the 6th term in there.
Oh, is the 6 terms in there? You're the best, because we only got to add the first what?
5.
The first 5 terms. So I'll take that out. This would keep it more accurate, the more terms we add, but we only have to add the first 5 terms. The first 5 terms. And Isaac, thank you. I'm going to make sure it's only these terms that we need to add to get this desired accuracy. So I'll go back in here and knock those out. We don't need that. Hey, if I kept it in there, it just gives it more accuracy. Does everyone understand that? The more terms we add, the more accurate we'll get. But we're saying we only need to add these first 5 terms here. I'll hit the light. Just so everyone can see. We only have to sum those first 5 terms to obtain an accuracy to be as close to the actual sum to be within there. And I'll do it again. I just want to see what that sum is. It's going to be very close to what we had before. Hey, what is the sum of L2 now? Close the brace. And 1.01730, and I don't give that accuracy. This is accurate. Having an error less than this. Cool. Now, did I put the negatives in there? Did I put the negatives on those?
No.
So I have to, that's the one thing I gotta be careful of, everyone. Would this be mathematically correct? Because I didn't have the what?
Negatives.
Were the negatives in there? Connor?
No.
So I gotta make sure I'm adding the what? The negative and the plus, and the negative and the plus. We gotta add those in there, true? So just make sure that I'm adding those into this. I can just go into that list and put those negatives on there. Which ones would those be? Second left. Was the second term negative?
Yeah.
Yep. So I'm just going to insert. Just a little negative symbol right there. No problem. What I'll do is I'll enter this again. That edit. I'll go up here and I'll just hit clear and hit enter. And I'll now just enter the actual formula. What was it? I'll type parentheses -1.
You're in the wrong spot.
Oh, let me get up to the next one, thanks. -1. Caret. This is raised to the,
X plus 1.
and I gotta do L1 plus 1, correct? L1. Plus 1. Now I'll write error down. What's this multiplied to?
It's divided by L1 to the 6th.
L1 to the 6th. Raised to the 6th. Now, and thanks for being patient, I do have to keep that in when I'm going to think about what's the actual sum, because this was negative and this was negative. This one was positive, this was positive. This one right here, first one, keeps alternating between the positive stuff. Positive, negative, positive, negative, positive. This was negative, but did we need this? No. All right. And now second quick. And I'll just say clear screen so we can focus on this. We are now going to sum number 5. Sum L2. And we now have the desired action, 0.98556. And that's how accurate we are. Cool. Hey, so try another one of these. Super job with this, everyone. I'll make sure to keep those negatives in there so we know that we're actually adding up the right terms. This one, how about -1 to the n? Over n factorial. I'm going to change the direction slightly. So this is what I have for this one. How many terms of the series do we need to add to be accurate to 4 decimal places? How many terms of the series we need to add to be accurate to 4 decimal places? And secondly, approximate the sum to 4 decimal places. All right. -1 to the n, all over n factorial. Well, we'll make a little chart here. And an ace of n, right? 1, 2, 3, 4, 5, 6. I don't know how far we're going to have to go, so I'm just going all the way out here. 7, 8. If we need more, I'll make another table. Hey, just plugging in a 1, what do you get? Is it positive or negative? What's 1 factorial? -1. Plug in a 2. 1 over 2. Plug in a 3. What's 3 factorial?
6.
So this is 0.5. What is -1/6 in the decimal point? What do you get from -1/6?
0.1667.
0.0667.
No, 0.1. 0.1667.
0.1667. Okay. And we'll just continue this, but I'm going to look for the what? 4 decimal places. What do we mean by that? And let's just think, when we see 4 decimal places, let's look to when we have a decimal point, and we have a 0, and a 0, and a 0, and a 0 at least. That sound good? That's what we're going to look for. So this could have like a, this could have a 9, 9 here. This is what we're looking for. Look for this when we get this to come up. So we have 4 decimal places. I'm not there yet, am I? Well, I'll use that screen. And I'll hit the lights. Clear. Clear screen. Let's do it again. It should be hard. I'm going to go to Stat Edit. Stat. Actually, I just did Enter. So Stat Enter. Up arrow, I'm going to hit Clear. Enter. Up arrow, hit Clear. Enter. 1, 2, 3, 4, 5, 6, 7, 8. That's far enough. Arrow right. So what do I type in here? Don't use X, use L1, right? I'm going to do parentheses. Yes.
You gotta jump up to the L2.
Oh, thank you so much. Wait, I gotta get that first one. Up arrow, and I'm in L2 right here, and I will do parentheses, -1, close the parentheses, raised to the L1, And now I have to divide what?
L1 factorial.
Where's the factorial? I'm going to hit L1 factorial. Where is it? So I hit, there's L1, everyone. I'm going to go to math, and then arrow over to probability, and it's the fourth one down. And I'll hit it. And I'm like, oh, cool. This way I can see a list and just concentrate. Now, keep in mind, if you don't like using this list, it's no problem just doing these on a blank screen, finding these numbers. Which number gives me a 0, 0, 0, 0? The 8th term. Aha. So when the 8th term gives me 2.5 e to the negative 5. 2.5 e to the negative 5. What's that in decimal form there, Andrew? What would that be? 2.5 e to the negative 5.
0.00002.
And when this is the first number where we had these 4 zeros in a row, isn't it? So which terms do I have to add up? This was the first number where we got that accuracy. We're going to add these numbers right here. Now make sure, negative, this is positive. Negative, this is positive. This will be negative, this will be positive, and this will be a what? Negative. So, I'm going to answer letter A right now. How many terms of the series do we need to add to be accurate to 4 decimal places? Is this correct? That's what I worry about on the test. Is that a correct answer? No. How many terms? The first 7 terms. So I'm going to make it 7. The 8th term was the first term that gave me that desired accuracy, so I need to add the first what? 7 terms. I'll even put the word term with it so you know. Does that make sense? Okay, good. And they want us to approximate the sum, so I'll go back to this. I'll make sure I got my negatives and positives this time, and I only have to add up the first 7, right? Hey, what if I accidentally leave that 8th term in there? Will I still be correct? I want to know that. Will it still be accurate? Yeah, the more terms you add, the more accurate it gets, right? We're just saying you only have to add this much.
So on a test, it's fine if you just don't.
Of course. Like, what if you accidentally, like, maybe someone missed this problem, but on this one, think about it here. What if they added the first 12 terms? They're going to be correct. Because it's going to be accurate to how many decimal places?
Okay, that's all.
It'll even be more accurate, but it'll be accurate to 4 decimal places. Does that make sense, everyone? The more terms you add, this is for who? The computer programmers. This is for the programmers who say, hey, you save time, and when you get the, just adding these terms, you get the desired accuracy. That's what we're talking about. All right, so I'll hit the light. I will knock out that 7th term, or excuse me, that 8th term. Even though I didn't have it. Do this sum. I'll go in here. Let's see. I'm going to delete that. I'm going to go over here and delete this. And when I have my negatives and my positive numbers in there, just to double check. Negative, positive, it's alternating. I just want to make sure we didn't forget that. Good. So I'll hit second quit or second mode. And I'll go to list. Whoops. Second. Stat. There we go. I'm going to go over to math. Use that summation button. And I'm going to sum which list? L2. And I only have to go to 4 decimal places, right? Negative 0.6321. That's my answer. Negative 0.6321. I do want to point out, what's the number after the 1? What if the number after the 1 was a 7? What should I do here in my final answer? Round up. 7 got that? You got it? Any questions on that? This theorem's awesome.
So in the case of like if we're doing this on the test, just like we put in like up to 10 terms and the list would be sum it.
It's going to be more accurate. Like I didn't have to delete that one, right?
Four are going to be the same. So.
Exactly. The more terms you add, the more accurate this will get. But it'll contain that accuracy that you want. The toughest thing, I think, is answering that question. That's the one we gotta be careful on, right? Juliet, that was the one we had to find. What was the actual place that we had to get that desired accuracy for the first time? How about that for the first time? But the more and more terms you add, it just gets more accurate. But we want to save time when it comes to programming. We want to save time. You don't add up to 100 every time. You only had to add 7 times. Hey, cool. Hey, great job. Hey, I'll turn this off. Hey, the last thing we do is the ratio test. Oh, you'll like this. The ratio test. Good job, everyone. Hey, if that list stuff bugs you, I get a lot of students over the years, they go, I don't like playing around with that. They just get them on the front screen, write them down until they get the number. And you'll notice, even with that, me working that thing off that computer, I'm used to working it off of what? This thing, it's so much easier to use like Microsoft Excel. You know, I used to be practicing this stuff at home, I know. It's easy to use something like Microsoft Excel to look at this stuff. Okay. So now, the ratio test. This test is outstanding. We're going to look at the limit as n approaches infinity of a ratio of a sub n plus 1 over a sub n in terms of some series. And we'll see if that limit exists. If the limit's less than 1, then the series is absolutely convergent. If the limit's greater than 1, the series is going to be divergent. If the ratio we get turns into a perfect 1, we can't use this test. We'll have to use another test. Okay? So if you fall in love with this test, just be careful. When you get a limit equal to 1, you can't use it. You're going to have to use one of the other tests. I have the word absolutely convergent here. And that always gets students going. They're like, why did you write that? So I'm going to talk about what absolutely convergent is. It's just a stronger phrase. It's a stronger phrase that can be used in terms of convergence. So I want to give an example of a series that isn't absolutely convergent. This one. And when that series right there is not absolutely convergent. But this series is convergent, isn't it? This series right here, is this convergent? It is. By what test? This converges by the alternating series test. Will you check it? It's alternating. The terms of these are what? Decreasing, right? And what's the limit? Let me hide that. What's the limit as n approaches infinity of b sub n? 0. So this is converging by the alternating series test. But I want you to tell me something. What if I do absolute value bars on this? If I do absolute value bars on this, what would you get? You'd get the summation of this. And what do you know about that series? This diverges because it's a what? It's our harmonic series. So what I'm saying is, this series right here, we can call, it's convergent, everyone. It is a convergent series by alternating series test. I just can't call it that. I can't state that it's absolutely convergent. All right. So to be absolutely convergent, we're saying you got a series that's already convergent. You can put absolute value bars on this portion, and that series is convergent. Cool. So that's what that absolutely means. All right. So let's look at a problem. Where can this be helpful? And when this is an 11.6. This is number 3 from 11.6. Equals 1 to infinity. We got an n over 5 to the n. And what I'd like us to do right now is think about all the other tests we've used so far, and then we'll apply this ratio test. Geometric series test. Can I use it? I want to see whether or not this converges or diverges. Is that geometric? Be careful. It's not because of the what? The n. Does that make sense? It has to be all exponential. I can't use that. How about test for divergence? Well, what's the limit of that sequence? Going to 0. I can't use that. How about the integral test? Anybody use the integral? Does anybody know how to integrate that? Right? I know we're sitting there going, oh, we don't integrate stuff like that. So this is where the ratio test can be really handy. I got a mixture of a polynomial or a monomial with an exponential. And none of these other ones are working for me. Integral test, test for divergence, GST. Ratio test can be very handy when you have some type of monomial mixed with an exponential. Or maybe a factorial with a monomial with an exponential. So what we do is, we start by taking a limit as n approaches infinity, put some absolute value bars, and you have to find a sub n plus 1. Do you know what I mean by a sub n plus 1? I need you to substitute. The word is substitute for n plus 1. So if you substitute n plus 1 there, what do you get? N plus 1 over 5 to the n plus 1. And I'll put a long fraction bar. So there's a sub n plus 1. Does everyone see what I did? I just substituted what? N plus 1 for every n. Now, underneath it, you just put the original a sub n sequence, which is n over 5 to the n. We're going to find this limit. And if this limit is less than 1, this series is convergent. If it's greater than 1, it's what? Divergent. So it's a cool test. How do you divide fractions?
What do you multiply?
So when I'm going to do that, I'm going to just take this n plus 1, 5 to the n plus 1, put a dot, flip that over, right? Hey, can I take off the bars now? Is this always going to be positive? Yeah, so I'm gonna, if you want, you can keep the bars there, but does everyone notice this would always be positive terms? Nice. Now, we need to, so how do you rewrite 5 to the n plus 1? Way to go, Adam. Did everyone hear this? I'm going to write 5 to the n plus 1. This is important. As 5 to the n times a 5. I'll use the electron. This is extremely important when doing the ratio test. Adam is doing that so he knows what cancels. So I rewrote 5 to the n plus 1 as what? 5 to the n times a 5. Like, how could you rewrite 7 to the n plus 1? How could you rewrite that? That's 7 to the n times a 7. I think you got it. Let me try one more. How would you write 11 to the n plus 2? I'm trying to get you. What would that be? 11 to the n times 11 squared. And if you're rusty on your old algebra, you know, just put that in your notes. I know. Hey, does anything cancel? So let's rewrite that, because it looks all sloppy. What do we have there? What's the limit of this? The worst thing is when a student does this math and they cancel things out correctly and then they tell me the wrong limit because their eyes missed something. It's all sloppy. Let's rewrite this. I've got an n plus 1 over an n. And what's that fraction right there? 1 what? Isn't that 1/5? Anybody know what this limit is? You can do L'Hopital's rule, bless you, or you can think of a rash, whoreass. Powers are the same. What's the whoreass? 1/5. Does everyone recognize this is the limit of this sequence right here?
Where did the 1/5 come
I just took that 5 and put 1/5 in front.
from? Oh, okay.
You could write it like this, but sometimes, Connor, that can bug you. You can sit there and go, but you may prefer that. You could have written it like this too. So if you, Connor, or anybody in here prefers to write this like this, that's totally fine. I'm going to write it both ways. I'm going to let you all choose which way you would prefer to look at this when you're finding the limit. Because the key is you just want to find that limit. Can I do L'Hopital's rule? Sure, what's the derivative of n plus 1? 1, what's the derivative of 5n? 5. 1/5. Or you might think, oh, there's a horizontal asymptote.